Welcome everyone. In today's session we are going to learn about a string matching algorithm which is widely known as Boyer-Moore-Horspool Algorithm. In this algorithm we take two inputs, one being a search keyword and the being a large string or a sentence, and we try to find out if the search keyword exists within the string or the sentence. And we do this by placing the search keyword alongside the sentence and comparing each character from right to left of the keyword. And when we find a mismatch between two respective characters, we skip the position of the search keyword by n number of steps. The value of n, or the number of steps or positions to skip, is decided by a bad match table, and we will learn to make this or create this bad match table in the coming up example. We are using a problem or an example to better understand this algorithm. In this problem, a small string and search keyword is given. For the part 1 of the problem, we would have to create a bad match table. And to create a bad match table, first we have to learn the formula of finding value of a current or given character. The formula is length minus index minus 1 in general. An exception is made if the keyword or the character is the last character of the given keyword. In that case, the length for itself is given as the value. And if the character isn't included in this keyword, we represent it as an asterisk sign. And the value given would be same length for. So let's try to work out for the current given keyword. First we start from the leftmost character, which is D. Its index position is 0. So we use it in our formula and find 4 minus 0 minus 1. So the value or the number of steps to be skipped if we encounter the character D as the mismatched character in the string would be 3. We repeat this process for L. We find the value 4 minus 1 minus 1, which is 2. Similarly, for R, we get 1. Now, when we encounter L again in the keyword, it is repeated. And we also see that L is at the last position of the given keyword. Hence, we are supposed to give the length 4. But since the last position keyword L already has a predefined value, which is 2, we are not going to reassign it as 4. We had to focus or give an importance to these rules, which is an exception. If the last keyword has been already assigned a value, or the last character has already been assigned a value, we should not modify or change. If we were to encounter a character repeated number of times, we can change the value in the match table unless it's the last character. Okay, so we next have to find the value for any other character other than the characters given in the keyword. For example, if we encounter the characters A, B, E or F, it should be represented by an asterisk in the bad match table, and we'll skip the 4 number of steps, and this 4 is taken from the length of the complete keyword. Now we have to move on to the part 2 of the solution, which is matching the keyword with a string. And here is where we use this bad match table. First we place the search keyword right below the string, and character by character we try to compare from right to left of the search keyword. So the first character to compare would be L, and when we compare we can see that it does not match with the corresponding character in the string. So we check the value of the character D in the bad match table. We can see that the value is given as 3. So we can skip 3 number of positions and end up in this format. Now we repeat this process and compare the L with R. If it was matched, we would have compared the next character R with L and do this process repeatedly. Since it is not matched, we can take the value of R from the bat match table, which is 1, and skip one step. Now when we compare it, we can see that it has been perfectly matched as L and L. So we do not need to skip. Now we match the next character R and R. We repeat this process till we find that all the characters has been matched. Now we can conclude that the search keyword has been found within the string. Now we can analyze the efficiency and complexity of this algorithm. So for the worst case scenario, this algorithm has a time complexity of m multiplied by n. This time complexity is same as the one produced by the naive algorithm, which is one of the most basic algorithm for string matching. And for the best case scenario, we have the result 10 time complexity of O of m by n. Now, even though the time complexities are similar to the naive algorithm, this algorithm is much better and faster since it can skip a number of steps, and especially in situations where a lot of different mismatches, it will be more efficient as we are skipping a lot of positions and hence we can find the result faster. Now that concludes our session, and I hope that everyone has understood the BMH algorithm. And thank you and have a nice day.